Hello everyone, welcome back. So today we are going to solve a problem related to arrays and dynamic programming. It's a very nice problem. So the problem name is coin change. Let's go through the problem. Here you are given an integer array in coins representing coins of different denominations and an integer amount representing total amount of money. Return the fewest number of coins that you need to make up that amount. If that amount of money cannot be made up by any combinations of the coins, return -1. You may assume that you have an infinite number of each kind of coin. Basically, we are given a coins array and one amount variable. We have to use those coins and basically create an amount out of it. And there are infinite number of each kind of coin available with us, so we can use any number of coins as much as we want. So coin of denomination 1, 2 and 5 are present of infinite numbers with us, so we can use them any number of times as much as we want. So but basically we have to make this amount variable by using the minimum number of coins possible. So what are the possible ways in which this 11 can be made? What if we just consider or take a coin of denomination 1 only? So in though that case I have to use 11 number of coins, right? But what if I use two coins of value 5 and one coin of value 1? So in that case I have to just use 3 coins. So the output that I have to return is 3. That is the minimum number of coins that I can use so that the amount sums up to 11. It's a very simple problem and very standard problem related to greedy and dynamic programming approach. So let's see like how this problem can be achieved or can be thought of approaching using the greedy approach. So I will consider one example. Let's take the example of, suppose the coins array given to us is 1, 3, 4 and 5, and the sum that we have to make is suppose 7, right? So the greedy approach, what does the greedy approach say over here? If we want to use the minimum number of coins, so this is the coins array. If we want to use the minimum number of coins, right? So uh, in that case we have to use a coin of highest value. So if you want to make a value of 7, so in that case firstly I should use a coin of value 5, right? So if I subtract 5 from 7, the value comes out to 2. Then I have to somehow make value 2 out of this coins array. I cannot use a coin of denomination 5. I cannot use 4 over here because 4 is greater than 2. Cannot use 3, but I can use coin 1. So if I use a coin 1, the remaining value that I have to make is still 1. Then I can again use a coin value 1, and the value I have to make now is 0, which means I have completed or created the value 7, right? So in this process, what are the coins I have used? I used a coin of value 5, I used a coin of value 1, then again 1. So the total number of coins in this case I have used is 3. But there is a catch over here, like this is not the solution that we are looking for. So 3 is a wrong solution, because we can make the value sum by using less number of coins less than 3. How can we do that? Suppose we just use a coin of value 3 and coin of value 4. In that case also the sum would be 7. So in this case we are just using only 2 coins, right? So answer will be 2. So the greedy approach won't work over here. So we can't basically select the highest denomination coin value and basically subtract that from the sum. So that is not feasible in this approach. So one of the other ways for this problem can be a recursive solution. So suppose over here I have to make value as 7, right? So if we go via depth first search approach, which is nothing but a recursion. So for to make a value 7, suppose I use a value coin of value 1, right? So if I use a coin of value 1, The remaining value I have to make is 6. The other possibility can be I use a value of coin of value 3. In that case, the remaining value is 4. If I use a coin of value 4 over here, then the remaining value is 3. And if I use a coin of value 5, the remaining value that I have to make is 2. Right, so let's go to the depth first search solution. So let's suppose we went to this branch of this recursion. So now I come to this 2 variable. What are the possibilities I have? See here as well, I will have 4 possibilities. That is, I can use any of these 4 coins. So suppose I used 1 over here. So from 2, if I suppose use 1, then what is the spending sum that I have to make? 1 only. Suppose I use 3 over here, but this is not a possible scenario. Like whenever I have to make a value as 2, I cannot use a coin of higher denomination that value, right? Suppose I have to make value of 7, then I cannot use a coin of value 8, right? So here the value would come out to be -1, which is a wrong case, so it won't be valid. Similarly, I can't use a coin of value 4 over here, because it will result into a value of -2. Similarly, I cannot use a value of 5 over here because it will result in -3. It is also not valid. So these 3 cases are not valid if I want to make a value of 2. So now coming back to this, now I have to compute what is the minimum number of coins I have to use to make value 1. How can I do that? Can I use a coin of value 1? Yes, I can. So if I suppose use a value of coin 1, the final value will come out to be 0, which means I have completed the creation of value 7 over here. If I am at 1, can I use a coin of value 3? No, I cannot, because the value will result out to be negative. So this is not a possible scenario. Same is the case with other 2 negative scenarios. If I use a coin of value 4 and 5 over here. Right. So this is one part of the solution. So if I at any point reach 0, which means that is one possible way of reaching the solution. So here, this is one of the ways I am reaching the solution. So what are the coins I have used in this particular scenario? So firstly I used 5, then I used a coin of value 1, then I again used a coin of value 1. So overall 3 coins are used. Right, so let's go through the other approaches as well, other parts of the tree basically. So suppose I was at this particular 4, right? So what are the possible ways I can go from this direction? So from 4 I can reach a coin of value 1, that would result in making the sum as 3. From 4 I can use a coin of value 3, so 4 minus 3 is 1. From 4 I can use a coin of value 4 as well, which would result it into a 0. From 4 as well, can I use a coin of value 5? No, I cannot, because it would result in a negative number. -5, it is not a possible scenario. So here I observe that I can reach a 0 value over here as well, right? So this is also one of the possible solutions. So here, what are the coins I have used? Firstly, I used 3, then I used 4. 3 and 4. So number of coins used is 2. Yeah. So now going to this part of the tree for 4. So here what I can see is from this one, I had actually already solved this part of the problem when I was at this particular one. So I actually, in recursion, I would actually recompute the same cases which I had already computed when I had traversed this part of the recursion. This part of the recursion basically. So here as well I will have the 4 cases -2, -3 and -4, which I had over here. Right. So if I use just normal recursion, I would be recomputing what I had previously already calculated. So when I had reached this particular one, this part of the recursion, I would be doing the same set of things which I had done previously. Right. So that's basically a one step in addition to what I had already done. So suppose also over here, when I'm this particular part of the recursion, from 3 I can use a coin of value 1, and the remaining sum that I have to create is 2. From 3 I can use coin value of 3, it is 0 over here. From 3 I can use a coin of 4, but it would result into -1, which means I don't have to go further into the recursion. From 3 I cannot use a coin of value 5 because it would result in a value negative, so I cannot use that. So if I go to this part of the solution, 3 2, so I'm encountering this 2 value again because I had solved for this particular 2 over here as well, right? So this whole tree is going to be created in the exact same way over here as well, right? So I am basically recomputing what I had already done. So that's the downside of recursion over here, that I am recomputing what I had already solved. Basically I have to divide this problem into sub problems, and in such a way that I don't recompute a particular part of the particular sub problem again, right? So if I have the solution of like basically over here, what it means is, suppose I have already solved this particular recursion. At this point I know that what is the minimum number of ways, what is the minimum number of coins I need to make a sum as 2, right? So can I maintain that already known information in a variable, so that when I reach this part of the recursion I can just use whatever I had already computed, right? So we have to divide our problem into smaller problems so that we can reuse what we had already calculated. So that's where the dynamics of programming comes into picture. So here we are going to use the bottom-up approach of DP. How are we going to use it? We will divide our problem into little sub problems, and basically we have to finally compute that what are the minimum number of ways I can reach 7, right? So why don't we start with, like, what are the ways I can compute or reach variable 6, right? So if I suppose already know what is the minimum number of coins needed to make a value 6, then I just add 1 to it, because 6 plus 1 would result into 7, right? So I can just reuse whatever information I already had while computing the coins needed to reach a value 6. So let's break this problem down into sub problems. So in DP, what usually we have is, like, we create one array, or it can be a 1D array or 2D array based on the problem. So here our requirement is, like, we can only fulfill our requirement just by creating a 1D array, right? So let's name the array that we are going to create as DP, and every index of this array, so this is a DP array, and every index of this array is going to denote what is the minimum number of coins needed to reach that particular index, right? So suppose this is the array, these are the index 0 1 2 3 4 4 5 6 and 7. So this particular element will tell me, DP of 0 would tell me what is the number of coins, minimum number of coins I need to make value 0. So in that case it is 0, because I don't need any coin to make a sum as 0. Then going to the next index, DP of 1, it denotes what is the minimum number of coins I need to make a sum as 1. So if I look over the input array, I can see I can directly use a coin 1, right? So in this case it would be just 1, because I can use a single coin of value 1 to make sum as 1. Then I go to DP of 2. How are we going to make sum 2? If sum value is 2, how are we going to reach it? So to reach a value 2, what are the possible ways? So I can use a coin of value 1, but I cannot use a value of coin 3, because 3 is greater than 2, right? So if I am using a coin of value 1 over here, right, so number of coins would be, if I use a coin value 1, so number of coins would be 1 coin plus the remaining sum would be 2 minus 1, which is 1. So I have to make a sum as 1 now. So sum value is 1, and I already know what is the minimum number of coins needed to make sum 1, which I have maintained over here. So I will just use this variable, which is nothing but dp of 1. So it is 2 over here. Similarly, dp of 3 would be, what is the minimum number of coins needed to reach a value 3? So it would be, if I use a coin 1 plus dp of 2, right? The other way can be, if instead of using a coin 1, what if I use a coin 3 over here, right? So if I use a coin 3, so the number of coins would be just 1, plus if I use coin 3, so the remaining I have to make is 0, so it would be dp of 0, right? So we have to take the minimum value of these two, which is 1 plus dp of 2 is 2, and 1 plus dp of 0 is 0. So in that case, the minimum of 3 and 1 is 1, right? So let's compute dp of 7, which is fine, which is our final aim, right? So dp of 7, how can we reach dp of 7? We can use coin 1 over here. So if I use coin 1, which means it would be 1 plus dp of 6. We have to take the minimum value of all these variables, 1 plus dp of 6, or if I use a coin of value 3, so number of coins would be 1 plus dp of 7 minus 3. Otherwise it can be 1 plus dp of 7 minus 4 if I use a coin of value 4, and otherwise if I use a coin of value 5, it would be dp of 7 minus 5. So I have to take the minimum of all these 4 values, and that would be the value of the dp of 7. And finally I will be returning whatever value is present in the 7th index of this dp array. I hope the solution is clear, but if it is not, let's try to code it and things would be clearer. So I would directly code in the dp approach. So in this dp I have to create one array in which I am going to maintain what is the minimum number of coins needed to reach a particular sum. So let's name the array as dp only, and the size of the array would be nothing but the amount that we are going to make plus 1. Size is plus 1, which means the last index value would be amount only, right? So I'm going to iterate over the, and one more thing is the dp of 0 would always be 0 because we don't need any coin to make a sum as 0. So I can directly put dp of 0 would be 0, and then I'm going to start from the first till the last index, which is amount. The last index is amount because the size of the array is amount plus 1. And then I'm going to write another loop which is going to iterate over the coins array so that I can take the minimum of all these values. That's what I have to check over here. Coins.size g++, and here I have to check if coins of j, if it is greater than I, right? So the value that I am going to create, if it is less than the coin value, that means I can't use that coin, right? So in that case it doesn't make sense to consider it while calculating the minimum. So I will directly continue the loop, and it is not necessary that the coins array is sorted, so that's why I have to check this condition. And I will create one variable which will help me to take the minimum value out of these. So I have to take the minimum value out of these 4 or whatever number of values we have. So I'm initializing this variable x, which is nothing but it is maintaining the minimum value, minimum number of coins to reach the ith sum. So it is initialized to maximum value, so it's fine. So here what I am going to do is I am going to update this x with the minimum value of dp of I minus coins of j and the existing value of x. So what I have done over here is, so if I want to make a sum as suppose 7, so suppose I value is 7, so 7 minus coins of j initially would be 1, then it would be 2, then 1, then 3, then 4, and then 7. So I'm taking the minimum value of dp of I would be 7, so 7 minus 1, then dp of 7 minus 3, then dp of 4, and dp of 7 minus 7, which is 0. So this is what it is going to be, right? So finally our x variable would be updated, and when I have iterated over all the coins in the coins vector, I am going to update this dp of I to be x, right? X plus 1, basically I have to use one extra coin, so that's what I am doing over here. Dp of I would be x plus 1, and finally I have to return dp of here it would be amount variable, nothing else. Yeah, so let's submit this, let's try to run this, let's see if there are any compilation issues. And this is fine. I'm trying to submit it. Okay, there is a runtime issue, dp of I, so okay, yeah, got it. So what I have to do over here is, like, I need to check whether if I'm able to use any of the coins or not. So it can be the case that I'm actually not able to use any of the coin, and I have initialized this variable x to int max, and suppose this if condition is all in all the cases it is executed and we never reach this particular statement, right? So in that case I am doing x plus 1, which is int max plus 1, so it doesn't make sense in that way. So I'm just checking if x is equal to int max, which means I am not able to use any of the coins. So in that case dp of I would remain int max only, and in the other cases dp of I can be x plus 1. Basically int max here is denoting that we are not able to use any of the coins to reach a particular sum. And yeah, let's submit it. I guess there is one more case that we are missing. Yeah, right. So suppose if the final amount that we are returning, so in the problem statement it has been mentioned that if the amount of money cannot be made up by any combination, then we have to return -1. But I am actually returning the int max value, which is wrong. So I can check if dp of amount is equal to int max, and in that case I can return -1. Otherwise, if it is not valid, then I will be returning dp of amount. Let's submit it. Yeah, the solution runtime and memory are also perfectly fine over here. So it's a like very simple problem related to the dynamic programming. So if you guys are not very comfortable how dynamic programming is basically used, so I will suggest you to go through some standard problems like 01 knapsack is there, this coin change problem is there, and other standard problems like related to palindromes is also there, right? Common subsequence, which is also one of the standard problems. So keep on practicing dynamic programming problems as well, and it's a very important concept from the point of view of interviews. And I will try to cover a lot more problems related to DPs in coming problems. So yeah, keep on practicing, and I will see you next time with another problem.